Thank you so much for the nice introduction. I am delighted to give this presentation today on clues about the breakup of the African continent. In the background, I have a photograph of a GPS station that's in Madagascar. It's in northern Madagascar. And it was one of the stations that's going to be central to the story I'll tell you today about breaking up the African continent and a lot of what we understand about how the African continent moves and deforms today, and what are some of the forces that are underlying the present day plate motions that we've observed with GPS. So this project has some contributions from Dr. Ella Faraha Saria from Tanzania, Corne Creamer at the University of Nevada, Reno, my former PhD student, Tahiri Rajan Arsen, who's now a researcher at the University of Antananarivo in Madagascar. Also, his former supervisor, Gerard Rambalamanana, and Rui Fernandez in Portugal as well. So this work has received funding from the National Science Foundation as well as National Geographic, and we've received technical support from UNAVCO. So I'd like to acknowledge those institutions as well. My presentation today has 5 parts. I'm going to talk about fair data principles, so that may be new for some of you. Then I'm going to go into an introduction about the East African Rift System. I'll talk about a paper that I published just last year on redefining the kinematics of the East African Rift System. And then I'll go into some work done by my former PhD student, Tahiri Rajan Arsen, about the forces that are driving present day motions in East Africa. And then I'll provide a summary. So let's talk about fair data principles first. So FAIR stands for findable, accessible, interoperable, and reusable. These principles were published by Wilkeson et al. In 2016. And so the idea is that when you publish data, you can put it into a repository that makes it available for other scientists to use. So repositories such as Pangea, Zenodo, IRIS, UNAVCO, and then, so there's many repositories out there. Even Open Science Framework is another one that we've used. And I bring this up because a lot of publishers are adopting fair data principles, including the American Geophysical Union. So if you ever need a place to put your data, and even software is becoming fair as well, I'm providing you a website here. It's repositoryfinder.datasite.org. You can go to this website and search for repositories that may be appropriate for your data set. So like Pangea is a nice general repository for earth sciences data. Zenodo is more broad. It covers all different disciplines. IRIS is great for seismic data and also some other data as well. UNAVCO is great for geodetic derived velocity solutions and also raw data sets. So these are a few examples that we've used in my group. So for this particular work, there have been a lot of institutions who have made GPS and GNSS data available to the community, and a lot of their logos are listed here. So I'd like to give recognition to these institutions who have made the work that I'll present today possible. Okay, so let's talk about the East African Rift System. This is a nice map that shows topography in the background, where every place that's over 1,000 meters in height is blue. So this is showing that East Africa and Southern Africa is quite high relative to the surrounding areas. The East African Rift System is the active divergent plate boundary between the Nubian plate to the west and the Somalian plate to the east. It's quite broad, so it stretches north-south all the way from the intersection of the Red Sea and the Gulf of Aden down to south of South Africa at the mid-oceanic, the Southwest Indian spreading ridge down here. And then it also stretches east-west from Eastern Congo all the way to Eastern Madagascar. We know the rates of extension fairly well from geodetic observations. It's about 1 or less than 1 millimeter per year in the south, and it increases up to about 6 millimeters per year in the north. We know now that there are at least 4 microplates between the Nubian plate and the Somalian plate. So we know there's a Victoria microplate, a Rovuma microplate, and the Luanda microplate. And just recently, the sand plate was resolved by Wedmore et al. In 2021. So that's a new one that's quite recent. The East African Rift System is seismically active. I'm showing here a subset of earthquakes from the NEIC catalog just for the East African Rift region as red circles. And we're also quite aware that the East African Rift System is volcanically active, with the majority of volcanoes happening on the eastern branch. So you can see the vast majority of volcanoes are here, and there's a few sparse volcanoes what's called the western branch. And there's also a few quaternary volcanoes in Madagascar as well. So I would like to note that you may see in the literature East African Rift versus East African Rift System. And generally when people are talking about the East African Rift, they're focused on the continental portion of the entire system as a whole. So I just wanted to point that out, and I'll use that terminology later in this talk too. So that's a nice overview of the East African Rift System. Now let's talk about this recent paper that I published in Geology just last year. So kinematics refers to how the tectonic plates move and deform, and also the geometry of the tectonic plates. There was some early work by Stein and Gordon in 1994. They suggested that the East African Rift System was wide and diffuse. So that means all of the deformation was not localized, but it was actually spread across the entire system. So this red region and this yellow region here. Later in 2002, Chris Hartnedy suggested, based on the distribution of seismicity, which is shown as these gray bands, he suggested that instead of a wide diffuse zone, that the East African Rift System was broken into several relatively aseismic blocks, such as the Rovuma and the Luando blocks. So these two very different models of the kinematics of the East African Rift System have been tested several times over the years. Now, in order to differentiate between these two models, we can take physical observations of the surface motions with GNSS or GPS observations. So we physically measure how the surface is moving. In the figure to the left, we have a map that shows in black vectors, these are actual GNSS, or these are GPS velocities in this map. And so using GPS velocities, we can determine if there are these aseismically, relatively aseismic blocks within this area. So using the GPS data, and here's another example from Wedmore et al. 2021, where GPS data were used all across the African continent and surroundings to resolve the sand plate, the Rovuma plate, and as well as differentiate it from the Nubian plate. So one other example of a kinematic model that uses GNSS observations, or specifically GPS, this one from Soria et al. In 2014, he resolved the Victoria, Rovuma, and Luando plate using GPS observations. So a little bit about the GPS system. It stands for Global Positioning System. It is one of many global navigation satellite systems. So you may be hearing more the term GNSS, and I'll use that term sometimes interchangeably with GPS. But GPS is specifically the US constellation. There's GLONASS, Galileo, there's Beidou, there's several others that exist. But this one, most of what I'll talk about today is based on the GPS system. So to measure the surface motions for the work I'll present today, we are focused on GPS. This figure to the left is showing the Earth in the middle, and a constellation of an example of how the satellites orbit the Earth and their particular orbits here. So the GPS system is operated by the US military. It is approximately 35 operational satellites orbiting the Earth, plus or minus a few extras. They transmit radio signals down to the Earth's surface, and this image to the left is giving an example of how 4 satellites are transmitting radio signals to the Earth's surface. And then we use the GPS phase equation to get really high precision positions and velocities. So I just want to point out a couple of things in this equation. So the ion portion and the troposphere portion, ion stands for ionospheric delay, and troposphere stands for tropospheric delay. And these are example parts of this equation that let you know there's a lot of corrections that have to be made for the propagation of the GPS signal as it goes from the satellite down to the Earth's surface. So the ionosphere has a lot of electrons in it, and that actually can slow down the GPS signal. And the troposphere has a lot of water vapor in it. So we do a number of corrections to make sure that we can get a very precise signal. So there's a couple of different types of research grade software. There's Gamut Globe K, Bernice, Gypsy X. These are a couple of examples that are that do the corrections that make it possible to get millimeter precision positions and velocities. So I'm a Gamut Globe K user, just like Bob Smalley at Siri. So once we process the data, in our case, we process it with Gamut Globe K, we get time series. So in this figure, we have time along the x-axis in day of year. So there's 365 or 366 days in a year, depending on if it's a leap year. And then we have displacement in this time series along the y-axis. So here in each of these blue circles represents one position per day with a standard error associated with it. So once we have our time series, we can essentially, it's a little more complicated, but essentially use the distance equation, the velocity equation, distance over time, to calculate the velocity at each station. So what do these stations actually look like in the field? On the left, we have a continuous GPS or GNSS station. This is one I installed in Uganda just a couple of weeks ago. This is right near Queen Elizabeth National Park. We actually saw elephants in the background. It was so amazing while we were putting up the station. Fortunately, it's on a hill, so you don't have to worry about the elephants coming up here. Another type, so we have two types of GPS stations. There's continuous. So these are installed in bedrock, ideally installed in bedrock, and they're measuring your GPS signals or GNSS signals all the time at 15 or 30-second intervals or even higher frequency. And then there's campaign GPS. This is an example from Madagascar in 2010, where we set up the station for about 72 hours or hopefully a little bit longer. And then we take the instrument down and we come back a year or two later, measure that same position for 72 hours or a little bit longer. And then we figure out how far that position moved over the time frame in which we made the observations. So these two different types, there's a number of factors that determine whether or not you use continuous or campaign GPS, but both are capable of getting you those millimeter precision positions and velocities. So how do we obtain this GPS data? So I wanted to give you a little bit of idea of what it's like in the field when you're actually collecting this data. So sometimes you have a lot of traffic. So we're even honking at the sheep. This is in Tanzania a few years ago, and you know, it's not the only place in the world where we deal with such traffic. We also have dealt with baboons in the road. So we think these baboons may have been having some kind of conference. I mean, there are so many of them, and they just loved hanging out in the road. This was just in January, a couple of weeks ago, that we experienced hundreds of baboons on the road, like over and over again. It was pretty wild. And then in Kenya, we've dealt with camels, you know, having to deal with this traffic as well. And then sometimes we do have to deal with very dangerous animals. So this was also in Kenya.
Move back again. No, they are hungry. Move back a little. Oh, there it is. Now you can open. Now you can open.
Is that inside the park? Is that like a national park that you are in?
So this one, yes, this one was inside a park. All the other ones were not inside of a park. Let's watch that one more time. It's always amazing to see this. Yeah.
Oh, there it is.
And sometimes we do work in parks. So in Uganda, we were working in a park. Yeah, it was quite incredible. Okay, so once we, just to be on a more serious note, what is it actually like? We find bedrock when we're searching for these stations, and we drill into the bedrock with a pretty powerful hammer drill. And then we install a benchmark. And so it's for campaign GPS, it is a benchmark that we're measuring over and over again. So these stay in the rock, and then we're figuring out how far these benchmarks move over time. And then we set up our instruments and we level them very accurately over and over again to make sure it's very level. These are some students from Madagascar I'm working with, teaching them these skills. And then this is one of our complete setups in Madagascar, where we have a solar panel. We have a tribrac that helps us keep it level. We have a box over here on the right that has a battery in it and a GPS receiver here. We have cables connecting things. So the solar panel charges the battery, and then the battery powers the GPS receiver. And then as an example, we also install continuous stations. This is one in Tanzania where we have a different type of monumentation. So in some places, bedrock is not available. So this is called a shallow braced monument, where we dig down about 6 meters and in all directions here. And so it ends up being a very stable monument, even though it's in volcanic sediments or volcanic ash. So this one is actually measuring volcanic deformation in real time, and it transmits all the data open access to NAVCO and also an online portal. So you see our radio transmitter over here too, and we also have a seismometer at this site. Okay, so that's what it's like. That's the reality of some of the field work. It's also a lot of fun. So we do have students having a blast, and here Rija is quite excited about having drilled his first hole for the benchmark. So we do have a lot of fun in the field too, even though it is a lot of hard work and there's a lot of traffic you have to deal with. Okay, so back to the science, back to the scientific questions. I'm going to address 2 questions with this particular paper that was published. So where is the Luanda-Somalia plate boundary? So I have this image from Saria et al. 2013 on the left, and he put the plate boundary right through the middle of Madagascar. But it should be dashed because it's not particularly clear where that boundary is located. And then based on an earlier paper, I discovered that it's likely this model here has the Somalian plate moving too slowly. So I've also investigated a new rotation rate for the Somalian plate, or a new angular velocity vector for the Somalian plate. So let's take a closer look at Madagascar, because this is important for this work. This is a nice geologic map of Madagascar that has a few components highlighted. In yellow, there's quaternary sedimentary structures, and then in red are quaternary volcanic structures. So let's first focus on the rift basins that are here. There's the Alautra-Anke rift. The Alautra-Anke rift up here in kind of northern central, kind of central eastern Madagascar. We've got the Morondava Basin that's extending, and then there's some hypotheses that suggest the Ranatzaru shear zone has been reactivated and is extending. And then there's also this quaternary volcanism. So Madagascar itself is tectonically active. It has been in the quaternary. And then it also is seismically active. These are a few focal mechanisms from the Global Centroid Moment Tensor Catalog that show largely extensional focal mechanisms with one strike slip and then one thrust event. There's been a more recent paper published in 2020 by Rakendrabe et al. So they found, they used a network called the Makamo network, which was a seismic network that covered Madagascar as well as the Comoros. And this is Tsitsi. She relocated several earthquakes in this region and also found a much broader distribution in the red circles of seismicity across Madagascar. So further showing that Madagascar is tectonically active, and that the seismicity is pretty complex with a lot of the seismic activity extensional. Now, with respect to the plate boundary, there have been several published models. Kusky et al. In 2010 suggested that pretty much most of Western Madagascar was diffuse and deforming. Argus et al. In 2011 put the plate boundary kind of through South Central and then over to the west in Madagascar. I showed you the Soria et al. Boundary. And then in 2018, I published a paper that just made all of Madagascar deforming. So there's some conflicting, ideas about where this plate boundary exists, or even if there is a plate boundary, like maybe Madagascar is just deforming. So in order to test this hypothesis, I developed a new velocity solution for Madagascar and surroundings. I focused on the Somalian plate and the Lawandle plate for this paper. So I processed 25 GPS stations that were used in a kinematic model. 16 of the sites are continuous and were originally predicted to be on the Somalian plate. And those are some of the ones shown in red. And then 5 were episodic GPS stations. So those are some shown in yellow. And then 3 continuous sites are on Madagascar. In this figure, if it's yellow, then the station has not been used in the past for kinematic modeling. But if it's red, then the station has been used in the past. So that's what these colors mean in the figure to the left. So we had 1 station on Comoros, MAYG, that was also new. But I note that I did not process data after May in 2018 because there was some volcanic and seismic events that were happening in that region. And I didn't want to confuse the tectonic signal with that information. So I processed the data with Gamma Globe K using a 3-step approach that's pretty well established. Something that I used that was different from the previous approaches is I used the code called Hector to model white noise and flicker noise for all of the sites. And then I also applied the Gauss-Markov equation for time correlated noise using Hector for the continuous stations. So these noise models are how these ellipses were defined. So I tried to be quite meticulous about the noise models. And then finally, for the kinematic model, I required that sites with 1 sigma uncertainties less than 1.5 millimeters per year, so they had to meet this threshold in order to be included in the kinematic model, which is all of these stations shown here. So the horizontal velocity field is available in a Nubia fixed reference frame as a supplement to my paper. And the supplement is on Figshare. I've included all the model files, all the input files and output files, which includes a file that has the velocities in a PSVelo format. And then also the files are available at UNAVCO through FTP, the velocity solution. So I did my best to make this paper fair. All the model files and data files are available. And it has been, interestingly, it has been downloaded like, I think over 800 times now, which is kind of cool. All right, so what did I do to actually test the hypothesis? Well, I needed to build a kinematic block model. I used the code tDefNode, which is openly available at this website. And the way tDefNode works is you define regions like are shown here on the left. You define a few elastic blocks, and then you define the boundaries between those blocks as simulated faults. And you can estimate angular velocities. So like Euler poles, you can estimate the rotation of the rate and angular rotation of the angular rotation of the blocks, and as well as the full angular velocity vector. And then you can also do fault locking with tDefNode. Now I chose not to do fault locking for this model because I was very focused on the plate motions and resolving the plate geometries and the plate motions. I was not specifically interested in the fault locking at this stage. So I did a linear inversion of the GPS velocities for the angular velocity vectors. Now, as I mentioned before, all of these files are available on Figshare. So what our model consists of is 4 blocks that were constrained by Soria et al. Or fixed, And then I varied the Lawandle microplate and the Somalian plate. So I varied the geometry and then also the number of velocities that were used to constrain those two plates so that I could determine if Madagascar was indeed moving with the Somalian plate or if it was moving with the Lawandle plate and where exactly that boundary exists across Madagascar. So to test the hypothesis, I first have to create a base model of the Somalian plate. So I used the statistics developed or published in McCaffrey in 2005. I used the reduced chi-square, I used the weighted root mean square and the normalized root mean square. Those statistics are shown up here at the top. So these are my base statistics that I'll be comparing subsequent experiments with. So one experiment was, does Madagascar move rigidly with the Somalian plate? So I added all the velocities on Madagascar to this base model and determined using statistics if we got an improvement in fit or even a statistically significant improvement in fit. And the answer was no, nothing improved. There was no improvement in fit statistically. So that means the entire island of Madagascar does not move with the Somalian plate. So then I did further experimentation and I tested each site on Madagascar and the Comoros individually. So the Comoros site here did not improve the fit. So the Comoros are not moving with the Somalian plate. But it turns out there are 3 stations on Madagascar that had similar or better statistics when we compared with the Somalian plate base model. And those sites are shown here. So ABPO, ANTA, and VOIM, all of these were consistent with Somalian plate motion. So what does this mean with respect to interpretation of the plate boundary? So it's what I'm showing on the figure to the left are the residual velocities. So these 3 that were that matched Somalia plate motion, their residuals are randomized and quite small, whereas the residuals of the other stations on the island are more consistent with diffuse deformation. So the modeling suggests a broad deforming zone in most of Madagascar, and that there's a small piece that moves with the Somalian plate. And this is fairly consistent with the seismic distribution, as the seismicity distribution as well. So there's less seismicity in this small region over to the east, and there's a lot of deformation, a lot of seismic activity in central and northern Madagascar, which would be consistent with diffuse deformation. So we still have the question of, does southern Madagascar move with Lawandle? Because we have 2 sites down here that might be consistent with the rotation of a Lawandle plate going clockwise relative to Nubia. So doing some further tests, I bring in some additional data from the Southwest Indian Spreading Ridge because we only have 2 GNSS stations in southern Madagascar that might be on the Lawandle plate. So I bring in the spreading rate data as well as the transform azimuths. And so I test if we get a significantly better fit when we include a Lawandle plate. And I use the F test, which was published by Stein and Gordon in 1994 for testing if you get an improved fit when you include more tectonic blocks. And indeed, we do get a statistically better fit when we include the Lawandle plate. So in the figure on the left, we have only Somalia plate motion, which includes the geologic data and then the 2 sites in Madagascar, as well as the 3 that are consistent with Somalia plate. And then we get, if we include the Lawandle plate, which is the figure to the right, the F test indicates that the Lawandle microplate is warranted. So it is statistically significantly improved when we include the Lawandle plate. On these maps, we also have 2 Euler poles. So the yellow Euler pole is the Lawandle Euler pole with respect to Nubian plate. And then in the figure, in the red star is the Somalia plate Euler pole relative to Nubia. So for the kinematic summary, we found that the Somalian plate actually does move faster than previous estimates at 0.76 degrees per million years. We found that the Luando-Somalia plate boundary is in southern Madagascar through here, and that Luando plate rotates at 0.045 degrees per million years. And then we found that southern Madagascar indeed moves with the Luando plate, and that there's a broad deforming zone across much of Madagascar, extending across the Comoros. So the figure to the right shows the configuration of the final kinematic model from this work, which does not include the sand plate because we were focused on the eastern part of the East African Rift system. So now I'm going to move on to dynamics, and I'm going to talk about the role of lithospheric buoyancy forces on the East African Rift system. So if we think about the three major forces that are acting on tectonic plates, we have lithospheric buoyancy forces, and these are due to gravitational potential energy gradients that are caused by topography and density variations within the lithosphere. We have mantle tractions that are due to the interaction of sublithospheric mantle convection with the base of the lithosphere. Those can be vertical or horizontal. And then we also have subduction related forces like slab pull. And since Africa is mostly surrounded by spreading ridges, there's no major influence of slab pull on East Africa. So this image at the bottom is showing a description of the three major forces, and that slab pull is not a major role in East Africa. So that means the problem reduces to two major forces. So we can actually do geodynamic modeling by isolating one of the two major forces and determining if one of those forces is a major driver. So a couple of reminders about the East African Rift. This is the continental portion of the East African Rift system. It does have unusually high topography. Everything that's in a tan color is greater than 1,000 meters above sea level. So that means that there's going to be an influence of gravitational potential energy gradients, which generate lithospheric buoyancy forces. Some other interesting observations in East Africa are that there's GPS observations shown in blue that have a rift parallel northward component of motion relative to the Nubian plate. So there's a couple in the north that are showing this along rift motion. There's a few in the western branch over here showing this along rift motion. And there's a couple in the eastern branch that also have a component of northward movement to them. So this is anomalous when we look at the large scale plate motions, which are shown by the red vectors and the yellow vectors. So these are the predictions from kinematic models that are based on GPS data that are away from the deforming zones. So most of these blue vectors are in the deforming zones and showing a type of plate motion that's different, or a type of surface motion that's different from the large scale plate motions. Now, the driving forces of the east-west extension, which is represented by the red vectors and the yellow vectors, it is highly debated. So there's many authors, including myself, that have suggested lithospheric buoyancy forces dominate the east-west motion. But there's another group of scientists that suggest horizontal mantle tractions from some upwelling mantle flow, upwelling and diverging mantle flow are the major driving forces in this system. So what we're going to do in this portion of the talk is describe some geodynamic simulations that are three-dimensional and focus on testing if lithospheric buoyancy forces can drive the present-day plate motions that we see. Before I get there, a couple of other observations that are quite interesting. So the strike-slip focal mechanisms are highlighted by these focal mechanisms here. So there are several places along the East African Rift system where we're getting strike-slip focal mechanisms, which is consistent with this rift parallel motion that we're seeing from the GNSS or GPS observations. And then also an interesting observation is the seismic anisotropy. So if you're not familiar with seismic anisotropy, it can be a proxy for the interaction of the asthenospheric flow with the lithosphere. And so it's been hypothesized by Bagley and Nyblade that we have this upwelling, northward flowing mantle plume beneath Africa that is generating all of the seismic and anisotropy observations that are seen in this image to the left as the red bars. So the figure to the right is showing a tomography model of this upwelling plume structure, and then overlaid on that is the topography with the seismic and anisotropy observations as well. So they suggested that it's the flow of the African superplume interacting with the base of the lithosphere that generates these seismic and anisotropy observations. So for this work, we ask a key question, what is the relative role of lithospheric buoyancy forces compared to horizontal mantle tractions in driving observed deformation in the East African Rift? And we hypothesize that forces driving east-west opening of the Nubia-Somalia plate system are dominated by lithospheric buoyancy forces. So to test this hypothesis and answer this question, we use the geodynamic code aspect, which stands for advanced solver for problems in Earth's convection. We're using the Boussinesq approximation to solve the Stokes flow equations for incompressible flow, and we solve the conservation of momentum and the conservation of mass equations, which are shown here. Similar to my geology paper, we've made all the files needed to reproduce this work available. These are on Zenodo. And then also the model output files are on Open Science Framework because there's a limit on the size of files you can put on Zenodo. So we had to find a different repository, and Open Science Framework allows you to have some pretty large archives and pretty large files. So for this 3D geodynamic model that my student developed, he had a synthetic lithospheric thickness, which is shown in this figure to the right. So he used seismic observations to create averages of the lithospheric thickness for different regions of the rift system. So if it's in the eastern branch, it's 70 kilometers thick. If it's in the western branch, it's 90 kilometers thick. The cratonic regions, these are 150 kilometers thick. And then everywhere else, like the mobile belts and the other parts of the lithosphere, he made 100 kilometers thick. The ridges, so they're shown in red, the mid-oceanic ridges are 50 kilometers thick for the lithosphere. We also imposed topography from eTopo 1, and we used a second order polynomial interpolation at the surface to implement topography onto the mesh of aspects. And this map on the right is showing low topography in blue and high topography in red. And so this was actually what was input into the model. Some other assumptions that were made are about crustal thickness. So we used crust 1.0. In the figure A here, this is the base of the upper crust where red is lower or thinner crust and blue is thicker upper crust. In B, this is the base of the middle crust. So again, red is thinner middle crust and blue is thicker middle crust. And then finally, the base of the lower crust is shown in C with the same color scale. So we have variability across the crustal thickness, which again is based on crust 1.0. And then we take the input from crust 1.0 for density as well. So the upper crustal density is shown in A, the middle crustal density is shown in B, and the lower crustal density is shown in C, where the red colors are the lower density features and the blue colors are the higher density parts of the crust. Another assumption that's made is about the density of the mantle lithosphere. So we decide to isostatically compensate the model down to 100 kilometers depth. And we do that by laterally varying the density in the lithospheric mantle. So this figure to the right is showing the mantle lithosphere density, which you can see is laterally variable. And this was the density that was necessary to isostatically compensate the model down to 100 kilometers. Below the mantle lithosphere, it's a constant 3,300 kilograms per meters cubed for the density. And in this image, if it's blue, it's higher density, and if it's red or yellow, it's lower density. We also impose a conductive temperature geotherm for the lithosphere. And then below the lithosphere, and we use the Chapman 1986 equation. Then below the lithosphere, it's an adiabatic geothermal gradient. So there's two examples of the geothermal gradients shown on the right here. So if it's a craton, they're 150 kilometers thick. So we have the conductive temperature gradient up to 150 kilometers thick. And then below that, it's an increase, an adiabatic increase. For the rift domain, this was at 50 kilometers thick. So you have the conductive geotherm to 50 kilometers thick, and then the adiabatic increase below that. I show here for reference the different material parameters that were used in this model as well. Here is a nice 3D image of the viscosity structure that results from all of these assumptions and inputs. So for the viscosity, we use a viscoplastic rheology for the crust. The lithospheric mantle is dislocation creep, and then below the lithospheric mantle, it's composite rheology. So it's a mix of dislocation creep and diffusion creep below the lithosphere. So we can see that we do resolve the asthenosphere. That's this red area. And we have the lowest viscosity is 1 e to the 18th Pascal seconds, which is reasonable for the asthenosphere. And you can see the variability in the viscosity across the different parts of the model. So the model itself is 3,300 kilometers north-south. It's 5,300 kilometers east-west, and it goes down to the base of the transition zone at 660 kilometers. For the modelers in the room, we use quadrature finite elements for the temperature fields, compositional fields, and velocity fields. And the resolution of each grid cell is about 40 by 25 by 5 kilometers. So we're including the lithosphere, asthenosphere, and the transition zone in this 3D geodynamic model. So for some results, the lithospheric buoyancy forces that are arising from gravitational potential energy gradients, these are related to variations in topography and density. So here on the left, I'm showing the vertically integrated gravitational potential energy in teranewtons per meters from the model. So this is from Rajanarasan 2021. If it is a white color or a brown color, it's relatively higher than the blue colors. And then for comparison, this is a model that was 2D, but had some similar assumptions implemented with respect to isostatic compensation. This one is from my 2014 paper, where we had much lower resolution constraints, like we used eTopo 5 instead of eTopo 1, and we used CRUST 2.0 instead of CRUST 1.0. So the magnitudes are similar, but the what was resolved in Rajanarasan et al. It's just much finer resolution because he used more finer resolution inputs. So these are some results that show two things. So in the figure to the left, figure A, we have as the red arrows, we have the predicted motions from the actual geodynamic model. And then the yellow arrows are predicted motions from a kinematic model. So we're using those more as observations to compare with the geodynamic model. And we find a very good fit of our model that's based on lithospheric buoyancy forces with the large scale plate motions. For the Victoria block here, we even get this counterclockwise rotation just with lithospheric buoyancy forces. For the Rovuma block, we also get a clockwise rotation of the Rovuma block with just lithospheric buoyancy forces. And then we get the clockwise rotation at about the same rate for the Somalian plate with just lithospheric buoyancy forces. Now, where the match gets poorer is in the deforming zones, where we have the rift parallel motions. So we are showing the RMS, the root mean square statistic. So it's much worse in the deforming zones, which suggests that there's some other forces at play here. Likely those mantle tractions are playing a role in the deforming zones. So a few more comparisons. We looked at the dynamic strain rate and compared that with the geodetic strain rate model of Stamps et al. 2018. So that's the one in the middle. So the dynamic strain rate is shown in A for this model, and then the residual is shown in C. So it's low strain rates and low residuals as blue, and then higher strain rates in red. So we do actually get a fairly good fit in the deforming zones for the strain rates. It's just the actual surface motions. So the magnitude of it's likely that the actual surface motions have some component of motion from the mantle tractions. So our key result is that lithospheric buoyancy forces are the dominant driver of deformation, but in the deforming zones, something else is likely at play. So to summarize the geodynamics, we have variations in lithospheric buoyancy forces driving the large-scale east-west extension across the East African Rift, and that results from the rigid block rotation. These findings are consistent with previous 2D models of regional deformation patterns. And then we suggest that viscous coupling to horizontal mantle flow may play a role in driving the deforming zone deformation. So my final conclusions, this figure to the left is showing predicted motions from the Stamps et al. 2021 kinematic model in as white vectors, and then the actual dynamic simulation, the predicted motions from the Rajan-Arsen dynamic model as black vectors. And then topography is in the background. So I've shown you a new kinematic model of the East African Rift system. I've shown you that variations in lithospheric buoyancy forces likely are the dominant driver of the east-west extension across East Africa. And then it's likely that viscous coupling to horizontal mantle flow plays a role in driving deformation in the deforming zones. So this is the conclusion of my talk. I would be happy to take questions now.
Hey, Sarah, this is Randy.
Yes.
So is the eastern boundary of the Somalian plate